Hello class. In this video we're going to talk about minimums, maximums, and end behavior of polynomial functions. Now the first thing we're going to do as we get started with this video is talk about limit notation. The limit is an idea in math where we talk about approaching a value instead of something being equal to a value. So this notation right here is the limit as x approaches infinity of f of x. So I'll write that out. Oh, don't have my pen selected. So the limit as x approaches infinity of f of x. So that just basically means our x values are getting higher and higher and higher. Okay. Now, right below it, it's the limit as x approaches negative infinity, which means our values are getting smaller and smaller and smaller. So as we look, if we were to look at a graph on a coordinate plane, sorry, let me make that a little bit neater. Okay. As we go off further and further to the right, what's going to be the end behavior of the graph? What is it doing? What is the graph telling us it's doing? And as we go further and further to the left, same idea. Okay, so let's go ahead and look at some polynomial functions. Okay, now what I've got here in the table is is kind of a generic way of putting it. I've got x to the even power plus and dot dot dot. This would indicate that there are more terms to come. And what I've got here indicated as even or odd is just the degree. Remember, the degree is whatever is the highest exponent within the polynomial. Okay. Now, generally, when you have an even degree polynomial, you get something that looks a bit like this. It's going to be U-shaped in some way, shape, or form, unless you've got additional terms, in which case it could be more like a W or something like that. Okay. Now, when we are heading to the right, when x is getting bigger and bigger, we look at this arrow here and we notice it's pointing in an upward direction. This means as x gets bigger and bigger and bigger, the function is also getting bigger and bigger. So the limit heads off to infinity. Okay. Likewise, as we head to the left, this other arrow here is indicating an upward direction, which means we are also going to infinity. Okay. Now for the next one, we got an odd degree polynomial. So this might look something like this. So as we go bigger and bigger and bigger on the x-axis, this arrow right here is indicating that we are going in an upward direction. So the limit as x approaches infinity means the function also heads to infinity. Now, the one difference here is that when we head off to the left, our arrow is pointing downwards, and that means we are headed towards negative infinity. Now, what I've got here is the negative even and the negative odd, meaning, sorry, that's probably not the best way to put that. If we reflected it across the x-axis. Now, if we think about it, if we reflect across the x-axis, this polynomial is now facing downward. So an even degree polynomial would now have the arrows pointing downward instead of upward. So my limits would be negative infinity and negative infinity. And if we flipped the odd degree polynomial about, sorry, it's not writing very well. There we go. About the x-axis, we would now get the opposite reaction, which means we would have negative infinity. There we go. And positive infinity. Okay. So kind of keep that in mind. This is a general set of rules that we can follow, and we don't even need to be looking at the graph. Now, we will be looking at the graph because we are also going to be looking at minimums and maximums, but if you were strictly asked about end behavior, you now have the tools to be able to do those problems without pulling up Desmos and without entering the function. Okay. But for the minimums and maximums, we'll go ahead and look at it. So min, max, and end behavior. Now, really quickly, just looking at the function behavior. Today's not my day for spelling. There we go. We can see that it's an even degree polynomial. The lead coefficient is positive, which means our end behaviors. It's not my day for writing either. Hold on. That the limits will both be positive infinity. Now let's go ahead. If you don't have your Desmos open, take the time now, pause the video, and go ahead and do that. So here's our first function. Let's go ahead and click on the points. We got one at 0, 3. That's a maximum. And then look at, we'll round these to the nearest tenth as we see fit. The minimums are both at negative 0.9, 0.9, and at 0.9, 0.9. Okay. Let's go back. My minimums were at negative 0.9, comma 0.9, and 0.9, comma 0.9. Oop. And those were absolute minimums, but we don't necessarily need to note that right now. And then our maximum, which was a local maximum, was 0, 3. So that's all we're doing in today's video. Okay. So let's go ahead and go on to the next example. So I'm going to go ahead, hide this one, show this one, and let's go ahead and zoom out a bit. Whoa, that's big. There we go. Okay. We got a minimum at negative 0.3 and negative 3.6. So let's go ahead and write that down. We got a minimum at negative 0.3, comma 3.6, and we had a maximum at, let's see what we got here, 4.9 and 67. Okay, 4.9, 67. Now the end behavior, we've got an odd degree with the 3, and we've got a lead coefficient that's negative. So that means as x approaches infinity, we're headed off to infinity. As we head off, oh, sorry, no, we're flipping it. Forgot to flip it. As we head off to infinity, the function heads off to negative infinity. And then as we head off towards negative infinity, the function itself will go to infinity. Okay. Let's go ahead and work on the third one. There we go. Similar looking graph here. Different values. We got a relative minimum at negative 0.2 and negative 4.3. So a minimum at negative 0.2, comma negative 4.3. And a maximum at a 4.9 and a 61.1. 4.9 and a 61.1. Now, similarly, we have an odd degree, and even though we're mixed up terms here, our lead coefficient is still negative, so our end behavior is precisely exactly the same as it was in the last. As x approaches infinity, the function heads to negative infinity, and as x approaches negative infinity, the function heads towards positive infinity. Okay. Last problem. All right, let's go ahead and zoom in on this one. We got that maximum, we got that maximum, and we got, oh, nope, that's the y-intercept. There we go. All right, so we got an absolute maximum at negative 1.1 and 10.3. So a maximum at negative 1.1 and 10.3. Okay, let's go ahead and we have 1.5 and 9.1 is another maximum, this time a local maximum. So sorry, that was 1.5, 9.1. 1.5, 9.1. There we go. And now let's go get our local minimum, which is at 0.3 and 6.7. Sorry, I forgot that one really easily. 0.3, 6.7. 0.3, 6.7. And now looking at our end behavior, we have an even degree and we have a lead coefficient that's negative, which means both of our end behaviors are headed towards negative infinity. All right, let's go ahead and look at one last example that'll be on your homework. This is an example going over how to write a function, a polynomial function from the graph, and we're just going to write it in function notation, okay? If my pen will work. There we go. Okay. What we do is we look at the x-intercept. So I have an x-intercept at -3, at -2, and I got one at 1. Now recall our transformations. These would indicate a 2-unit shift, a 3-unit shift, both to the left, and then a 1-unit shift to the right. So we're going to write them out as x minus, but if we take x minus -3, that's going to simplify to x plus 3. Likewise, x minus a -2 would be x plus 2. And then we're going to do x minus 1. And we got to think, does our end behavior match what we want? Well, we've got as x approaches infinity, this one heads off to infinity. And then as x approaches negative infinity, our function heads off to negative infinity. So we do not need to make a lead coefficient that's negative. But the fact that we have 3 terms indicates that this is an odd degree polynomial, which is what the graph also indicates, because we've got that general shape where one end is heading to infinity and the other end is heading towards negative infinity. But checking out the ends tells us if we need a negative lead coefficient, which means we would just tack on a negative in front of the polynomial. Okay, and actually we'd probably write a constant so that we can cover all our bases. But if this had been flipped around, we would put it. But this is our final answer. Remember that we are not done with the notes just yet. We do have one more day of notes. So if you come across something in the homework that we did not cover in this video, remember, we're going over that in the future. Thanks for watching.